Hello, so this is the second FRQ from the AP Chem exam in 2025. This first part asks calculate the mole. Okay, so if it's 2.883 grams, you can just use it divided by 18.2. This is the molar mass of water. You can calculate it by doing 2 times 1.008, which is the H2 part, and then add the O, which is 16. Or you can just, memorize it, I guess. I don't know. It comes up quite often, so it might be good. If you do 2.83 divided by 18.02, you get 0.15998, which, if we're rounding 4 sig figs, is going to be 0.1600 moles of water. This is your answer to part 1 of A. And then part 2 is combustion analysis. Okay, so we can start with the ratios, which is x, y, x, as you can see from the bottom there. And we know that we get 0.24 moles of carbon from the CO2 and equal amounts of oxygen. To find the ratio for hydrogen, you can just look at the amount of water produced and multiply by 2. From that, you can do 32 over 0.24, which is 4/3, and that's our ratio for C to H to O. So our final answer, we get C3H4O3. Calculate the molar concentration of the sorbic acid solution. For these kinds of questions, I think it's important to start by looking at what information they give you in the question itself, and then to look for the equivalence point. That's just where it goes up really quickly all of a sudden. And then using the information you get from that point, you can just finish the rest of your calculations, cross-multiplying to get the moles of base, and then since it's the equivalence point, that's also equal to the moles of acid you have. And then finally, you can find the concentration by dividing it by the volume, which is 10 mil. So to find the pKa of this next one, you have to look for the pH at the half equivalence point, which is at 8 mils, since our equivalence point is at 16, divided by 2 is 8. And the pH at our half EQ looks like about 4.1 or 4.2-ish, but don't worry too much about it because there's going to be wiggle room. For the last one, we're going to use Henderson-Hasselbalch, which I think is in the reference table, but it's just this formula that I'm writing out here. We can treat the inside like a variable that we're solving for because it's just asking for the ratio. Now this is just some simple algebra. You can solve for the ratio on the inside, which is 3.162. That's probably too many sig figs though, so I'm just going to go 3.2. So the rate law for the reaction. Okay, we can look at trials 1 and 3. Wait, I need space. There's no room to write. No. I'll write it on the top. Trials 1 and 3. Concentration of iodide is constant. Concentration of sorbic acid times 2 makes the rate times 2. If you want to explain it using more elaborate language, which you probably should, you can say that when you're comparing trials 1 and 3, the rate doubles when the concentration of ascorbic acid is doubled, while the triiodide ion concentration is constant. This indicates that the reaction is first order with respect to ascorbic acid. Something along those lines. Calculate the value of rate constant K for the reaction, including in your answer. So this one you can just pick one of the trials and just plug your numbers in. For the sake of being a boring person, I'm gonna use trial 1 and I'll write this out. So right here is 2.457 times 10 to the negative 4. This is your numerator, and your denominator is going to be 0.45 times 1.2. This gives you 4.55 times 10 to the power of negative 4. And for your units, you're going to look at this. Since rate is in molarity per second, which is also moles per liter per second, And then these two are both measured in molarities. And then you can just look at this and realize that you need a mole on the bottom and you need a liter on the top. I forgot to talk here, but you also need a second in the denominator, which like you can do second to the power of -1. So the final answer you will get here is liters per mole per second, which can be also written as molarity to the -1 times second to the -1. Like that's the same thing. So yeah. Okay. So basically, this is more soluble in water, but not normal iodine, which is like this one. Explain the difference. So our options here are pretty limited. So I just went down the list here. No hydrogen bonding because no hydrogen, no dipole because no polar, and then no LDFs because both of them have LDFs. These have. But there's also ion dipole, which would exist between this triiodide ion and water because, you know, triiodide is an ion and iodine is not. So your justification can just be like ion dipole. Oh, that's it. Hey. Okay. Good luck and have fun studying.